You're here because you want to master hydroxy compounds with a University of Cambridge graduate. Let's begin. As for every new functional group that we are learning, you have to know these three things. One is to memorize and understand your reagents and conditions for every reaction. Two is to understand and memorize your reaction mechanisms. So for this chapter, you will need to be referencing to a lot of mechanisms that are used in your previous chapters. And three, you need to understand the reasonings behind how the reactions work for this particular functional group. Your hydroxy compounds are mainly classified by the OH group over here. And these are further broken down into two main types of compounds. One is your aliphatic alcohols, and two, on the right, is your phenols. So how do we prepare our alcohols? We can do electrophilic addition of alkenes. For this, do refer to my alkenes lecture if you haven't already memorized the reagents and conditions involved, and the mechanism behind electrophilic addition. Next, we can do nucleophilic substitution of your halogenal alkanes. For this, it was already covered in the halogen derivatives chapter. So do refer to my lecture in order to memorize and understand the reagents and conditions involved, as well as the mechanism behind nucleophilic substitution, both SN1 and SN2. Now on to something new, it is the reduction of aldehydes and your ketones. So your aldehydes over here can be reduced to form your primary alcohols. And your ketones can also be reduced to form your secondary alcohols. You can think of reduction like just adding hydrogens across the double bond. Now the reagents and conditions for this reaction are LaAlH4 in dry ether at RTP, a very common reducing agent, or for this reaction specifically, we can also use NaBH4 in ethanol at room temperature and pressure. Another way to reduce is to use your hydrogen gas with your nickel, palladium, and platinum catalyst at room temperature and pressure. Your carboxylic acids can also be reduced to form your primary alcohol. And for the reagents and conditions, it's also LaAlH4 in dry ether at room temperature and pressure. Now what are some reactions that your alcohols can go through? Firstly, you of course will have combustion because that's expected for every organic reagent. So do refer to my mole concept lecture so that you can find out all the different calculations and equations that you have to come up with when you're doing a combustion question. Next, you can also do dehydration of your alcohols to get your alkenes. So do refer to my alkene lecture because it was also covered there, the reagents and conditions for this reaction. Next up, you can also do nucleophilic substitution to form your halogenal alkanes. This was also covered in my halogen derivatives chapter. So do refer to that so that you can know the mechanisms and the reagents and conditions for the reaction. Now on to something new, you can do oxidation of your primary alcohols. And this will give your aldehyde if you do immediate distillation and you use K2Cr2O7, specifically K2Cr2O7. You can't use KMNO4 for this reaction because KMNO4 is too strong an oxidizing agent. Next, what happens if you do use KMNO4 or you don't immediately distill your reaction if you use decremate 6 is that you will form your carboxylic acid instead. As you can already suspect, your aldehydes can oxidize further to give your carboxylic acids. The observations are, whenever you use decremate 6, it turns from orange to green. And whenever you use manganate, it turns from purple to colorless. You can just use these acronyms over here, DOG and MPC for MyPackCat. D is for decremate to orange to green, and MPC is manganate from purple to colorless. You can also have oxidation of your secondary alcohols, but these will turn into a ketone instead. Again, using the same reagents and conditions, which is your decremate 6 or your KMNO4, because these are your oxidizing agents, and you must heat. An exception for oxidation of your alcohols is when you're using a tertiary alcohol. Do take note that it cannot be oxidized. Now, a very common reaction that will get tested in your exams is the iodoform reaction. What is happening here is that this very specific boxed up group needs to be present in your alcohol, and then it can undergo this reaction according to these stoichiometric ratios to form your carboxylate anion. Now do take note of the ratios, and it might be better to memorize this whole equation itself so that you do not waste too much time during the exams. Now the reagents and conditions for this reaction are I2, NaOH aqueous, and heat. And as for the observations, which is important by the way, the brown I2 decolorizes and you'll form this pale yellow PPT, which is the CHI3 over here. Your alcohols can also form esters. So these actually undergo a nucleophilic acyl substitution. You don't really need to know the mechanism behind this, but you just need to know that your alcohols can react with carboxylic acids under these conditions, which is concentrated H2SO4 catalyst, or heating under reflux to form your ester. Now do take note that this is a reversible reaction. For stronger conditions, instead of a carboxylic acid, you can use your acyl chloride. And this will form your ester as well. And this is not a reversible reaction. This is a full reaction. And because these are both condensation reactions, according to the boxes that I've drawn, you can form your side products over here. Now next, we're going to talk about phenols. So your phenols actually have this OH group that is directly bonded to the benzene ring. And this is very important because it forms the underlying basis for most of the reactions of phenols. For your chemical reactions of phenols, of course again we have combustion, but more importantly, we have ester formations as well. So what's different about phenols compared to your aliphatic alcohols is that your phenols cannot react with carboxylic acids, but they can react with your acyl chlorides under the following conditions. You must use NaOH aqueous at RTP and then use the acyl chloride at RTP. So why is it that there is no reaction of your phenols with carboxylic acids? Well, it's because of this reasoning and this answering technique over here that you have to take note. The 2p orbital of your O atom in the OH overlaps with the pi electron cloud in the benzene. Because of this, the lone pair delocalizes into the benzene. And therefore, your lone pair is less available for donation to an electrophile. This makes phenol less nucleophilic, which is not what you want in a nucleophilic acyl substitution reaction. But it can react with your acyl chlorides, because your acyl chlorides are just stronger electrophiles compared to your carboxylic acids. For nucleophilic substitution using the OH, again with this same explanation over here, which is the 2b orbital of the O atom that is overlapping with the pi electron cloud, therefore the lone pair is delocalized into benzene. But also because of this, your CO bond is actually stronger because of partial double bond character. So take note that this same concept has been covered in halogenoarenes in your halogen derivatives chapter. So this is just a recap that due to this same concept and this partial double bond character, it requires more energy to break, and hence your nucleophilic substitution doesn't really occur with your phenols. Also, your benzene will repel the nucleophile due to the pi electron cloud. So it's very hard for the nucleophile to even come and attack the phenol when the nucleophile can't even approach. Your phenol has a benzene ring, so it can undergo electrophilic substitution as well. Now with this same principle over here, which is the 2b orbital of the O atom is overlapping with the pi electron cloud, so the lone pair of the O atom is delocalized into the benzene ring. Because of this, your OH group is actually an activating group. It's donating electrons to the benzene ring via resonance. And because of this, your benzene ring is actually more susceptible to electrophilic attack and hence electrophilic substitution. Your phenols actually only need milder conditions for your electrophilic substitution reactions to occur. Now do also remember that the OH group is 2,4 directing. If you ever forget that, do remember that you can always refer to the data booklet. So what are some of these reactions that involve electrophilic substitution? Well, you can have bromination. So you can add your Br2 and CCl4 and you can get mono-substituted products over here in the 2,4 position with bromine. Or you can use Br2 aqueous And you can actually get this multi-substituted product, which is very key to take note, by the way. For your observations, your orange Br2 will decolorize, and more importantly, you'll form this white PPT of your product over here. For nitration, you can use concentrated HNO3 and you get your multi-substituted product, or if you use dilute HNO3, you can get your monosubstituted products instead in the 2,4 position. Now, a very common question that comes out during exams is to compare the acidity of your ethanol, water, phenol, and your carboxylic acids. Well, let's break it down. If we look at the pKa's of each of these compounds, you will realize that the pK of ethanol is the highest. This also means that this is the weakest acid. Now, why is it so weak? Well, you have to look at the ion that comes from the dissociation. This ion, which is called the ethoxide ion, has electron donating R groups attached to the ion, the negatively charged O. For example, this one over here. Because of this, when you donate electrons to a negative charge, you're only going to intensify the negative charge. Therefore, your ion will just not be preferentially formed. Because of this, it's not very favorable for your ethanol to dissociate to give the ion. However, if you look at your phenol is a stronger acid than both your water and ethanol. And this is because of the same principle. The 2p orbital of the O atom in the OH is overlapping with the pi electron cloud in the benzene ring. Because of this, the lone pair delocalizes into the benzene ring. But more importantly, you have to look at the ion that comes out of it. So because of this, your negative charge can actually get delocalized into the benzene ring because the lone pair is delocalizing into the benzene ring. Your negative charge is going to get dispersed, and therefore, it's actually more stable for the ion because of resonance. And therefore, this ion is more preferentially formed. So the phenol will more likely dissociate to give H+ and this ion over here. So looking at this, you can actually get a very important concept. When looking at acidity in your organic chemistry module, you have to pay attention to the negative charge on the ions that will be formed from dissociation and determine if the ion is more stable or less stable, and therefore justifying your observations that you see. Your alcohols and phenols have also reactions with sodium and bases. For both your aliphatic alcohol and your phenol, you can both react with sodium. This is also a very good distinguishing test, and this will form your hydrogen gas. But your aliphatic alcohol cannot react with bases because it's just not acidic enough due to the explanation I just gave. But your phenols definitely can react with bases. For example, it can react with NaOH. It can also react with sodium carbonate. But take note that phenol, while it is acidic, it's just not acidic enough compared to carboxylic acid, for example. Hence, from your sodium carbonate, you wouldn't get carbon dioxide from this reaction. Lastly, you will have to know the distinguishing test for your alcohols and your phenols. For your aliphatic alcohols, it can undergo nucleophilic substitution, so again refer to a halogen derivatives lecture for this one. And it can also undergo acid-metal reaction with sodium, as I've covered just now. So you'll get your effervescence of H2 that gives a pop sound with a lighted splin. And it can also undergo oxidation, so refer to section A in the earlier parts of this video. For your phenols, it can undergo electrophilic substitution by Br2, so refer to section B, which I covered earlier just now as well. And it can also undergo this complex formation with neutral FeCl3. And this is very, very important. It often gets overlooked by students. Your solution will turn violet because of the formation of this complex over here. You don't have to memorize this equation or memorize the structure of this complex, but you just need to know that this reaction can occur. So that's all for hydroxy compounds. Again, I must emphasize that you need to memorize these three things and understand them if possible. One is your reagents and conditions, which you definitely have to memorize for all the reactions, and there's a lot of them for this chapter, so please memorize them. Two is to memorize and understand your reaction mechanisms. So in this chapter, it covers a lot of the reaction mechanisms that have been covered in your previous chapters, like your halogen derivatives, your arenes, and your alkenes. So do revise those if you need to. And three, you have to memorize and understand why reactions occur for this particular functional group. So for example, you see me keep on repeating why phenols cannot undergo certain reactions or why phenols undergo only certain reactions because of the 2p orbital and the delocalizing of the lone pair of electrons. So you always need to know these because you can be asked about any of these during the exam. If you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through your past papers and go through any doubts and clarifications you may have and show you why my class is the best fit for you. I'll see you in the next lesson.